This lecture is list as abstract data type. In a previous lesson, we introduced you to the concept of data structures, and we saw how we can talk about data structures in two ways. One is a mathematical and logical model that we term as an abstract data type, or ADT, and we also talk about data structures as concrete implementations. In this lesson, we will study one simple data structure. We will first define an abstract view of it, and then look at its implementation. And this data structure type is list. List is a real-world common entity. List is nothing but a collection of objects of the same type. We can have a list of words, we can have a list of names, or we can have a list of numbers. Let us first define list as an abstract data type. When we first define an abstract data type, we just define the data we will store, and we will define the operations available with the type, and do not go into the implementation details. Let us first define a very basic list. I want a list that can store a given number of elements for a given data type. This would be static list, and the number of elements in it would not change, and we would also know the number of elements before creating the list. We should be able to write or modify an element at any position in the list. Of course, we should be able to read an element in a particular position in the list. So I ask you for an implementation of such a list, and if you've taken a course in programming, then you should be like, hey, I know this. An array gives us its features. All of these operations are available with an array. We can create an array of any data type. So let's say we want to create a list of integers, so we declare an array as type integer, and then we specify the size as a parameter in the declaration. I can write or modify an element at a particular position. They can also read elements at a particular position. The element at the nth position is referred to AI. So array is a data structure that gives us implementation for this list. Now I want a list with many more features. I want it to handle more scenarios for me. So I'll redefine the list here. I don't want a static list. A static list is just a collection with a fixed size. I want a dynamic list that I can grow as per my needs. The features of my list are, I'll call my list empty if there are no elements in the list. I'll say that the size of the list is 0 if the list is empty. Then I can insert element into the list, and I can insert an element into any position in the list. I can remove an element from the list. I can count element in the list. And I should be able to read or write, or rather read or modify element at a particular position in the list. I should be able to specify the data type in the list. I should be able to define the data type when creating the list, whether it is a list of integers or string or float or whatever. Now I want a data structure in which an implementation of this dynamic list. So, how do I get it? Well, actually we can implement such dynamic lists using arrays. It is just that we have to write some more operations on top of arrays to provide for all these functionalities. So, let us see how to implement this particular list using arrays. Let's say, for the sake of simplicity, assume that the data type for this list is integer and that we are creating a dynamic list of integers. What can we do to implement such a list is to declare a really large array. As we know, the elements in the list are indexed. We'll define some of the index, declare an array of the max size. as A0, A1, A2, and goes on like this. So what I'll do is I'll declare a variable that will mark the end of the array of the list in this array. If the list is empty, we can set the variable to -1 because the lowest index possible is 0. So if end is -1, then the list is empty. End is pointing to -1, which is not valid. Now I insert an integer into the array. And let's say we do not say the position, and then the number is inserted at the tail or end of the list. So we will have an element at position 0, and now the index is at index 0. At any time, end marks the end of the list. Let's insert some more elements into the list. This arrow here, we insert a 4, a 6, a 7, and 9 into the list. This arrow here at the end of the list in the array. If I want to remove an element at a particular position, let's say I make a call to some function or something, I want to remove 2. At index 0 here, so to do so, after we remove the element, all other elements are shifted one place to the left toward the lower indices. It looks like we have implementation of a list on the left as described as the data type. We have the logic of calling the list empty. We have a variable end which is equal to -1. We can insert at a particular position in the list. We can remove an element. It's just that we have to do some more shifts in the array. We can count the number of elements in the list. It will equal to end plus 1. And we can read and modify at a particular position in the list. If we want to choose the data type, we can choose which data type we want in the declaration. This looks like a pretty cool implementation, except we have one problem. We said that the array will be of some large size, some max size, but what is a good max size? We can always exhaust the array. The data can grow to exhaust the array. In actuality, there is no good max size. So we needed to have a strategy for the scenario when the list will fill up the whole array. So what can we do in this case? We need to keep that into our design. We cannot extend an array. It is not possible to do so. We will have to create a new array, a larger array. So when the array is full, we will create a new larger array and then copy all of the elements from the previous array into the new array. And then we can free the memory from the previous array. So now the question is, how much do we increase the size of the new array? This whole operation of creating a new array, copying all of the elements from the previous array into the new array, is costly in terms of time, and a good design would be to avoid such costs. So the strategy that we choose is each time the array is full, we create a new array at double the size of the previous array. And why that is so, we will not be discussing in this lesson. This looks like a cool implementation. The study of data structures is not just about studying operations and implementation of these operations. It is also about analyzing the cost of these operations. So let us see what is the cost in terms of time for these operations that we have in the dynamic list. The access to any element in the dynamic list, if we want to access it using an index to read or write. And this we will take constant time. We have an array here, and in an array, the elements are arranged in one contiguous block of memory. Using the starting address or base address of the block of memory and the index or the position of the element, we can calculate the address of that particular element and access it in constant time. Big O notation that is used to describe the time complexity of operations for constant time is written as big O of 1. If we want to insert an element at the end of the array, the end of the list, then it too would be in constant time. If we want to insert at a particular position, then we would have to shift the elements to higher indices. In worst case scenario, if we inserted at the first position, we would have to shift all of the elements to the right. The time taken for insertion will be proportional to the length of the list. Let's say the length of the list is n. Or we can say that insertion is big O of n in terms of time complexity. Know that insertion is a linear function in terms of size of the list. Removing will again be big O of n. We said that insertion at the end of the list would be in constant time. This is not true if the array is full. Well, there is a good thing about this kind of implementation, and that is that we can access any of the elements in constant time, which is a property of the array. But if we have to insert some elements in the array, or we do have to remove some elements, then it will be costly. If the list grows and shrinks a lot, then we will have this thing of creating a new array and copying elements from the previous array to the new array again and again. And there is one more problem, is that a lot of the array would be unused. The memory would be of no use. The use of an array in terms of memory usage is not efficient. This leads us to think, can we have a data structure that will give us a dynamic list and use the memory more efficiently? We have one data structure that gives us a good utilization of memory, and this data structure is linked list. And we will study about this linked list in a future lesson. Until next time, see you.